Okay, guys, I forgot. Before we go to Runga Kutta, we actually want to talk about systems of differential equations. That's probably the easiest thing to talk about before we get to Runga Kutta, which is a really difficult topic. It's a little bit more complicated than Euler's method and Taylor's method to understand. Um, and I was going to derive Runga Kutta, but I don't think I'm going to do that. I'm gonna avoid that. If it was a regular class semester, I would probably go through and derive the formula for Runga Kutta, but we're not going to do that here, just for the sake of time and my sanity. Okay, so let's get started with systems of equations. This is going to be section 5.9, so we're going to skip ahead a little bit. Systems of equations. And what we want to do is we want to be able to approximate a system of equations. Approximate a system of equations. Okay. So let's do that here. Approximate systems of equations. And just like we approximated a solution to a regular differential equation, we can do the same thing for a system of equations. We can use Euler's method, we can use Taylor's method of order 1, 2, 3, 4, 5, whatever. We can use Runga Kutta method to do it. So it all works the same way in terms of how we construct a system of equations. So I'm going to do a system of equation using Euler's method and then with Taylor's method as well. And then you can extend the idea to Runga Kutta and so forth. So let's start off with our topics for the day. Okay, we're going to say, so system of equation using Euler's method. And then system of equation using Taylor's method. Or whatever order you want. So let's just start off pretty simple, pretty straightforward here. Suppose I have a system, just say we have a system of just two equations, which we'll call it x prime, which is equal to x prime, which is equal to f of x, y, and t. And then we have y prime, which is equal to g of x, y, and t. So what this means is that my system of equations, right, is in terms of three variables. I have two dependent variables, x and y, and then I have an independent variable, which is t, right? And so x and y prime, both of these guys depend on x, y, and t, or they can depend on x, y, and t. And then we have to have some initial conditions, right, because this is going to be an initial value problem, okay? It doesn't have to be an initial value problem, but just for simplicity, we're going to make it an initial value problem, where x of t sub 0 is equal to x naught, and y of t sub 0 is equal to y naught. So here, what we can do is that Euler's method extends very easily to this type of scenario. You essentially come up with an approximation for both x and y prime. X and y are solutions. So the solution for x will be x of n plus 1 equal to x of n, right? Just like we did before, plus it's going to be f of xn, yn, tn times h. Okay, so that takes care of the approximating the solution for x, and then I need to do approximation solution for y. Y sub n plus 1 is equal to, in this case, we have y sub n plus g sub xn, yn, t sub n times h. And then we have our initial conditions, right, that we had before, where we have x of t sub 0 is equal to x naught, y t sub 0 is equal to y naught. Okay. So this is Euler's method. Just kind of very similar to what we did before. If you guys remember with when we just had a single variable, right, we would just have one equation, and right, it would just be a function of just my one dependent variable and my independent variable. Here we have two dependent variables and one independent variable. I could extend this to three equations, 4 equations, 5 equations, 6 equations. It would extend the same way, right? H again is still my step size. What we have to be careful about is that when we use this Euler's method, right, we need to make sure that we solve, every time we do a step, we need to solve x and y both before we, so if we, x and y both before we go to the next one. So if I have x0, y0, I want to go to x1, y1, I need to solve, I want to go to x2, y2, I need to solve x1, y1 first before I can get to x2, y2, right? So I need to make sure I solve both of those first. I need to make sure I solve these guys simultaneously every single time I do it. Okay. Let's look at an example. I'm going to approximate, in this case, the solution to that's my my Outlook email making that beeping sound, so excuse that. You're going to hear all kinds of strange noises in the Wesley household. Right? So I have, in this case, I want to approximate the solution to x prime equals t plus x squared minus y. Y prime equals t squared minus x plus y squared. Okay? And I have x of 0 is equal to 3. Y sub 0 is equal to 2. Okay. All right. And I'm going to using Euler's method. That's what we're going to say. With h equal to 0.1. We'll use that h equal to 0.1 later. Let's just write down the formula for Euler's method first before we go any further. All right. So let's do it. Let's look at our first equation. So I want to be able to approximate a solution to the first one. I think that's t plus. Let me make sure that's t plus. Yep. T plus x squared minus y. Right. So for Euler's method, we have x of n plus 1 equal to, looking at the first equation that we have here, the first one, x of n, okay, plus my function on the right-hand side, I have t sub n plus x sub n squared minus y sub n times h. Okay. Y sub n plus 1 is equal to y sub n plus t sub n squared minus x sub n plus y sub n squared times h. Okay. Where my initial conditions are x of 0 is equal to 3 and y sub 0 is equal to 2. Okay, so this is my approximation to the system of equations using Euler's method. Let's look at the first couple of terms in this, right? Let's make a table here. Put the table over here. Give myself a little bit of space. So I have n t sub n, and then I have x sub n, y sub n. Okay, and so I have n equal to 0, let's say 1 and 2. So let's see, at n equals 0, t sub n is 0, right? And that's our t value at n equals 0. And then x sub n is 3, and y sub n is 2. So y sub 0 is 2. So x sub 0 is 2, and then x sub 0 is 3, and y sub 0 is 2. Let's plug in to find x of 1 and y sub 1. So x of 1, y sub 1. We use the h equals 0.1, so that'd be 0.1, 0.2 is what I want there. 0.1, 0.2. Okay, so let's plug in. X of 1 is going to be equal to x of 0, right? My previous term, which is going to be 3 plus the quantity t sub 0, which is 0, plus x of 0 squared, which is 3 squared, minus y sub 0, which is 2, times 0.1. Okay. And if you work that out, that is going to be 3.7. Would I get there? Okay. And if I want to, I can write 3.7 there, but I want to make sure that I do these together, x1 and y1 together. So I'm going to go x to y1. Y1 is going to be equal to y sub 0, which is 2, plus the quantity t sub 0, which is 0 squared, t sub 0 squared, minus x sub 0, minus 3, plus y sub 0 squared, which is going to be 2 squared, times 0.1. And when you work that out, you get 2.1. So I'm going to put that there, 3.7, 2.1. Okay. And then we're going to do x of 2 and y sub 2. We'll stop there. So x of 2, y sub 2. X of 2 is going to be, if we look at this one, x1. x1 is going to be 3.7 plus the quantity t sub 1, which is going to be 0.1, plus x of 1 squared, which is going to be 3.7 squared, minus y sub 1. Y sub 1 is 2.1 times 0.1. If we work that out, I have 4.869. Okay. And y sub 2 is very similar to that. Y sub 2, I should get 2.1, which is going to be my y1, plus the quantity 0.1 squared, okay, minus 3.7, okay, plus y sub 1 squared, which is going to be plus 2.1 squared times 0.1. And when I did this one, I got 2.172. So I can put that down. 3.7, so 4.869 and 2.172, right? So that's going to be my approximation. So I can say that x of 0.2 is approximately equal to 4.869, and y of 0.2 is approximately equal to 2.172. Okay. I mean, it's a rough approximation. We know that if we let our h value become smaller, we'll probably get a better approximation to this particular system of differential equations. But I want you guys to notice that if I were to try to solve this system of equations by hand, right, using the method that we've learned in differential equations, it would be difficult for me to be able to find a solution to this, right? But because we're using this kind of this numerical method or orders method to approximate the solution, that's much easier for us to do, all right? And we get a better approximation by using a different, using either a smaller h or a different method, like Taylor's method of order 4 or 5 or 6 or 2. Okay, so let's actually do that. Let's look at Taylor's method of order 2. And we'll do that right after this. I'm going to stop the video right here and we'll do Taylor method order 2.